Good evening, my YouTube viewers. It is Crystal here. I want to make the final video on distributions. And basically what we're going to do is we're going to create a chi-squared distribution and test it. So what you have to do is, because Python is just not able to work on formulas for several spreadsheets in one workbook, what you have to do is the particular spreadsheet that you are working on, you have to put that in a workbook called Work in Progress. And you just have your imported libraries as the first page and the spreadsheet that you're working on as the work in progress. And when you finish that, what you do is you go back to your main workbook and copy that page into the main workbook. That's the only way I've been able to solve the problem of Python not computing the values. Another problem that I had, which I haven't mentioned in previous videos, is if you'll notice, I have the hypothesis test on row 2 and not row 1. And the reason why that is because when I put the hypothesis test in row 1, it goes into error, and the only way I was able to correct that problem quickly was to move the hypothesis test into row 2, and that seemed to solve the problem. So if you are looking at my past videos, you may have wondered why I put it in row 2 and not row 1, and that is why. So what we're going to do now is we're going to look at the distribution of the chi-square. And so we'll come over here and we look at the code, the Python code. So it's a chi-square distribution. You set your parameters as degrees of freedom and sample size equals 2, 1000. So it's going to have 2 degrees of freedom. And then we generate the chi-square. So chi1 equals np.random.chi-square brackets degrees of freedom and sample size. And then we're going to plot the distribution using matplotline.pyplot as PLT. So plt.hist brackets chi1, comma, bins equals 30, comma, density equals true, alpha equals 0.6, color equals C, your X label is value, your Y label is frequency, and then we're going to show it. And you'll notice in cell C1, we've got a little right skewed distribution, and that is your chi-squared distribution. And I copied that code over into make chi2 and chi3. So instead of chi1, you had chi2 or chi3. And what I wanted to do is I wanted to check the means of these distributions. So mean 1 is 1.993, mean 2 is 2.0038, mean 3 is 1.9604. So you can see that the means are very close together. They're very similar. So we check the alpha, which is the, I think it's alpha is 0.05. So that is the point in the hypothesis test. So if the value is less than 0.05, then what you will do is you will reject the null hypothesis and accept the alternate hypothesis. Your null hypothesis are the samples are the same, and your alternate hypothesis are the samples are not the same. So in this instance, you're going to have to accept the null hypothesis because the samples are identical. The only difference in the samples is the name. But if you want to check the means, here you go, mean 1 equals chi1 dot mean, and we did the same thing with mean 2 and mean 3. So we're going to check the chi-squared contingency on one sample, and chi2 stat p-value DOF expected equals chi2 contingency, and we checked it on the first chi-squared distribution, so chi1 comma correction equals false. So we're going to print out the chi2 stat p-value, the degree of frequency, and the expected. So the chi2 stat is 0, the p-value is 1, and the degree of freedom is 0, and expected is an array. But the degree of freedom should be 2 because it was set up as a 2 when we ran the distribution, but this didn't accept that. So I'm not really happy with that reading. One thing that I have noticed is I have not been able to get the chi-squared to work on any of the distributions that I was working on, so I'm not really thrilled about that. And you would think that if you had a chi-squared distribution, that the chi-squared test would work on it, but the chi-squared test isn't working on it. So that's one little conundrum that I have. Now you've got the Kolmogorov-Smirnov test for 2 samples, and that seems to be the best test that I've been able to find, and I use that test in machine learning, and basically you use the test to find out if 2 samples are from the same distribution. So with the Kolmogorov-Smirnov test, a statistic p-value equals ks 2 sample chi1 and chi2, and then you print out the statistic and the p-value. And you also have, with the Kolmogorov-Smirnov test, you also have a 1 sample, but I didn't put that in there. I just put the 2 samples in there. You've got the Anderson-Darling test. Again, I'm not really happy with that, with the outcome. The Anderson-Darling test, I believe it's supposed to check if it's a normal distribution, and you can see that the normal AD function gives it away that they're looking for a normal distribution, and the chi-squared test isn't a normal distribution, it is a right-skewed distribution. So the statistics p-value equals normal AD, then chi1 axis equals 0. You print out your statistic and your p-value, so it's giving you a p-value of 0, which I'm not happy with that at all. So it's not a good test for chi-squared. And then we're going to do a likelihood ratio test, and it gives you, again, it gives you likelihood ratio test that gives you a null hypothesis, exponential distribution, null params, expon.fit chi1, null likelihood, log likelihood equals np.sum, expon.log pdf chi1 times null params. And then alternative hypothesis is a normal distribution. As an example, alt params equals norm.fit chi1, alt log likelihood equals np sum, norm log pdf chi1 times alt params. Calculate the likelihood ratio test statistic. LR statistic equals 2 times alt likelihood minus null log likelihood. P-value equals scipy.stats.norm SF brackets absolute value LR statistic, and then you print off your LR statistic and your p-value. So it gives you a p-value of 0. So I'm not happy with that. But the thing is this, again, this test is based upon a normal distribution, and the chi-square distribution is not a normal distribution. It is a right-skewed distribution. So the only test that we performed that had decent results was the Kolmogorov-Smirnov test. the rest of the tests didn't seem to work out very well. And so that's an example that you need to choose your test carefully, because if you don't choose the correct test for the distribution, then you're not going to get the outcome that you're looking for. But the Kolmogorov-Smirnov test is a non-parametric test, and it's the best test. So it says that the p-value is 0.93577. So that's what I'm going to go with. So that means we accept the null hypothesis. The rest of the tests, in my opinion, are not good tests for that particular distribution. But what I intend to do is I intend to do another series of videos on all of the hypothesis tests in SciPy and stats models. I'm not going to do the hypothesis test in Penguin because that's not a common library. So I've covered everything that I intended to cover. I covered the chi-squared distribution, the means of the chi-squared distribution, the alpha, which is the significance level. I've covered the hypothesis testing, and what the null hypothesis is and the alternate hypothesis is. And I've covered the fact that the Kolmogorov-Smirnov test is the test that I think is most reliable for this particular distribution. And I've also said that I'm really disappointed that the chi-squared test don't work on this distribution, because if it's a chi-squared distribution, wouldn't you think that a chi-squared test would be designed to work with it? So thank you so much for watching my video. If you like my video, please like and subscribe, and I look forward to making more videos about statistics for you in the future.